Hey everyone, and welcome to The Explainer. Have you ever actually stopped to think about how incredible it is that we can pinpoint a single tiny coffee shop in Tokyo or map the fastest route from your house to a completely unfamiliar city, all from a little device in our pockets? We completely take it for granted, but navigating our massive, spherical planet is literally a geographical masterpiece. Today, we're opening up the ultimate logical user manual for understanding planet Earth. We're going to look at exactly how humans figured out how to measure, map, and ultimately master our globe.
Well, to truly appreciate where we are today, we've got to look back, way back. Around the year 500 CE, the brilliant astronomer and mathematician Aryabhata wrote this exact quote: "Human beings have been absolutely fascinated by our spherical world for centuries. We've known for a really long time that we live on a floating globe in space. But knowing it's a sphere and actually figuring out how to locate ourselves on it, right, those are two very, very different challenges."
Okay, let's dive into this. Here's our roadmap for today. 1. Maps and their components. 2. Mapping a spherical Earth. 3. Coordinates and latitudes. 4. Longitudes and time zones. And 5. Putting it into practice.
Section 1. Maps and their components. The local problem. Before we can even think about mapping the globe, we have to understand the basic tool of the trade. Think of a map as your trusty, real-world treasure guide. Its entire purpose is just to show you where things are and to solve those everyday navigational challenges.
So picture this. Imagine you're visiting a new city for the very first time. You've just stepped off the train at the railway station and you desperately need to find the bank. How do you get there? Well, your spatial awareness immediately kicks in. You've got to evaluate the distance, figure out the direction using compass points, and read the visual symbols representing things like the hospital, the market, or school. This right here is the fundamental power of a map.
Now, while every map uses those basic components of distance, direction, and symbols, the specific treasure you're hunting for totally changes the kind of map you need. They generally fall into 3 distinct categories. You've got physical maps, showcasing natural surface features like oceans and mountains. You have political maps, which draw those invisible human lines, our countries, states, and city boundaries. And finally, you have thematic maps, focusing on specific data, like rainfall or population density. You're always looking at a surface from the top down, but the story completely changes based on the category.
And that brings us to Section 2, Mapping a Spherical Earth, the macro problem. Moving from that local perspective to the macro perspective introduces an immense, almost impossible geometric challenge.
And this brilliantly illustrates the massive headache early cartographers faced. As Aryabhata pointed out centuries ago, our planet is spherical. Well, actually, scratch that. It's slightly flattened at the poles, but it's essentially a sphere. The problem? Paper is flat. And, as it turns out, representing a perfect 3D sphere accurately on a flat 2D sheet of paper is physically impossible.
If you don't believe me, try this experiment at home. Take an orange and peel it so you have 3 or 4 large pieces of skin. Now, lay them on a table and try to press them completely flat. What happens? You can't do it without tearing them at the edges. The exact same thing happens when you try to force the entire surface of the Earth onto a flat map.
So, this leaves us with a massive question. How do we reliably map a sphere without completely distorting everyone's location? If physical flattening is impossible, we're going to need a mathematical solution.
Let's move to Section 3, Coordinates and Latitudes, the grid solution. To find any location, you need a grid. Think about a standard chessboard. You've got letters from A to H along the bottom and numbers 1 to 8 up the side. If you open the game by moving a pawn 2 squares forward, you simply say the piece moved from D2 to D4. It's precise, it's exact, and literally anyone in the world can replicate it.
That chessboard logic, that is exactly what we call a system of coordinates. A coordinate system relies on intersecting lines to pinpoint a location. The exact same logic that locates a pawn at square D4 on a chessboard is what locates a massive city on a global map. We just need to draw those imaginary lines all over our globe.
But to draw a grid, you've got to have a starting line, right? On Earth, our absolutely crucial starting metric is 0 degrees. If you take a globe and find the exact halfway point between the North Pole and the South Pole, you get a massive circle running all the way around the middle. This is the equator, sitting perfectly at 0 degrees latitude. From this baseline, we draw parallel imaginary lines, kind of like horizontal slices, moving north and south. Because the Earth is a sphere, these circles get smaller and smaller until they shrink down to exactly 90 degrees at the north and south poles.
What's absolutely amazing here is that these horizontal latitudes aren't just, arbitrary numbers on a page. They literally dictate how you live. There's a direct connection between your latitude and your climate. At 0 degrees, the equator, the sun illuminates the Earth directly, creating a hot, torrid climate. But as your latitude increases and you travel up toward 90 degrees, the climate becomes moderate and eventually freezing and frigid at the poles. Just by reading a map's horizontal latitude, you immediately know what jacket to pack.
So latitudes give us our horizontal slices. But to make a complete grid, we obviously need vertical slices too. Welcome to Section 4, Longitudes and Time Zones, the time solution. Now what's really interesting about this is that the vertical lines do way more than just map space. They actually dictate our clocks.
Just like the equator is the 0 point for our horizontal lines, we desperately needed a 0 point for our vertical lines, which we call longitudes. But unlike the equator, there is no natural middle for a vertical line on a spinning globe. So in the year 1884, global nations simply got together and agreed to draw a line in the sand. They decided that the meridian passing through Greenwich, an area of London, would be the international standard, 0 degrees longitude, the prime meridian.
From that zero line in Greenwich, we measure distances eastward and westward up to 180 degrees. Let's look at how this works in practice. New York sits at 74 degrees west. Over in the other direction, Delhi is at 77 degrees east, and Tokyo pushes way out to 140 degrees east. These vertical lines slice the Earth up just like wedges of an apple.
And here is where the math becomes absolute magic. The Earth rotates, right? So when it's breakfast in one country, people are fast asleep in another. To measure longitude is to literally measure time. Because of how fast the Earth spins, every 15 degrees of longitude equals exactly 1 hour of local time. If it's 12 noon at Greenwich, when you move 15 degrees east, it's 1 p.m. Move 30 degrees east, it's 2 p.m. If you move west, you subtract time. We have mathematically constructed our global time zones using these 15-degree geographical wedges. It's incredible.
Now, if you look closely at a map of global time zones, you'll probably notice the lines aren't perfectly straight vertical slices. They zigzag. Why? Well, because mapping has to respect human reality. A 15-degree straight line might cut a single country right in half, which would be an absolute nightmare for train schedules and businesses. So the time zones bend around international borders. The zigzagging continues all the way around the back of the globe to 180 degrees, directly opposite the prime meridian. That line is the international date line, where crossing it actually changes the calendar date by an entire day.
So the crucial point is that a map is not just a drawing. It's a mathematical tool that captures climate, time, and distance on a floating sphere. Let's shift from theory to reality in Section 5. Putting it into practice, your turn. I want to challenge you to be an active map maker today.
We've talked all about distance, grids, and scales. So here's a practical calculation directly from our source material. If you look at a map of India, and the map's legend tells you the scale is 2.5 centimeters equals 500 real-world kilometers, how would you calculate the actual distance between the estuary of the Narmada River and the estuary of the Ganga River? Grab an atlas, find that scale, and see if you have the geometrical tools to decode the actual size of our planet. Good luck out there, and thanks for exploring with us.